PAHs are formed by the incomplete combustion of organic materials such as coal tar. Many have been classified as human carcinogens with a mutagenic mode of action. Risk assessments employ potency equivalence factors, or PEFs, which convert the concentration of a selected PAH into that of a reference compound, in this case BAP. Human exposures to PAHs characteristically involve complex mixtures in the environment, and most available data pertains only to the individual compounds, making hazard and risk assessments challenging. To overcome this, these assessments assume dose additivity, meaning the total hazard of the mixture is equivalent to the sum of the contributions from only 8 prioritized PAHs within the mixture. As cancer data is expensive to produce, we believe mutagenicity data can be a cost-effective alternative to calculate PEFs for any mutagenic carcinogen. Our objectives were to determine tissue-specific PEFs using mutagenicity dose-response data, and to investigate the validity of the dose addition assumption using defined synthetic as well as complex PAH mixtures. Objective 1 was to determine tissue-specific PEFs. In this graph, black represents the reference compound BAP, and red represents our selected PAH. Here, the calculated PEF and the upper and lower confidence intervals can be seen. As you can see, DBHA and BPF are less potent than BAP in the small intestine and stomach, respectively, resulting in PEFs less than 1. Here you can see the dose-response data of all prioritized PAHs relative to BAP in the small intestine. Black triangles represent BAP. Curves to the left indicate PAHs with a potency greater than BAP and a resulting PEF greater than 1. To the right, PAHs with a lesser potency than BAP, with their response elicited by chrysine being the lowest. This plot demonstrates the PEF values with confidence intervals. The red dotted line indicates where BAP would be. PAHs with the greatest potency are on the bottom right, and the lowest are in the top left. Table 2 provides a summary of the PEFs calculated across all 5 tissues, and in Table 3, you can see that our mutagenicity-based PEF values align well with those calculated using cancer data. Objective 2 was to investigate the validity of the dose addition assumption using synthetic mixtures composed of only 8 prioritized PAHs, as well as complex mixtures, which often contain hundreds of PAHs. This plot represents the response data for all 8 PAHs relative to BAP in the bone marrow. The black line represents the dose addition prediction line. Mixture responses can be seen in red stars. When the response deviates from the prediction line, the response also deviates from additivity. In this case, you can see the responses are well aligned with the prediction line, indicating that the dose addition prediction holds true for synthetic mixtures. Similar results can be seen when following the same approach using complex mixtures with only slight tissue-specific deviations. Objective 3 was comparing BMDs of BAP equivalent synthetic mixes as well as complex mixes. Here you can see the dose response data for the complex mix versus the synthetic mixture. In this table, I've summarized the BMDs, comparing the BMDs of synthetic mixtures to its matched complex mixture. Red text indicates where the confidence intervals do not overlap. Overall, mutagenicity dose response data is a cost-effective alternative to cancer data and can provide PEFs for any compound in any tissue. We have also demonstrated that synthetic and complex mixtures elicit responses that are consistent with the assumption of dose addition. Our next steps are to analyze mutagenicity dose response data to determine PEFs and to scrutinize the dose addition assumption for other classes of compounds. Thank you.